Imagine deploying an autonomous AI agent to handle your company's vendor payments. The agent initiates a $5,000 transaction, but the bank's API times out before sending a response. To the agent, silence means failure. Its core instructions dictate that if an action doesn't successfully complete, it needs to try again to fulfill its goal, so it submits the payment again and again. The agent swarms the endpoint with repeated requests, entirely unaware that the first payment actually went through, and so did the next 5, draining $30,000 in seconds. This happens because standard software systems often rely on at least once delivery models. They are designed to guarantee a message gets sent, but they do not natively understand when to stop a hyper-persistent autonomous entity. Autonomous agents run a 5-stage loop: perceive, reason, plan, act, and observe. But an API timeout severs the connection between action and observation. Flying blind, the reasoning engine defaults to a continuous retry loop. Without a mechanism to check its physical actions against reality, the very persistence that makes an agent useful turns it into an unchecked, budget-draining liability. The core issue here is a mismatch in state. The large language model generates text to plan a theoretical action, but the physical infrastructure actually moves the money. To bridge this gap, we have to build a commit gate. This is a definitive boundary that separates the act of deciding to do something from the physical finalization of that action. When an agent hits an error and retries a task without a commit gate, the system processes that retry as a completely new, isolated event. It has no memory that it just attempted the exact same transfer 3 seconds ago. Step 1 to fixing this is modifying the agent's tool schema. Before it executes an action, the agent generates a unique intent ID for that specific subtask, injecting it directly into the request. That identifier links the agent's attempts together. If the agent retries the action, it sends the exact same intent ID. The infrastructure can now recognize that these scattered attempts actually belong to a single logical objective. Next, we install terminal rules at the orchestrator level. These are hard mathematical maximums on how many iterations an agent can run, preventing infinite recursion regardless of what the language model decides. Giving the agent's task an identity provides visibility, but stopping the runaway execution requires a rigid physical boundary in your architecture. That rigid boundary requires backing the agent's external actions with a transactional database. We have to take state control out of the language model's hands entirely. This introduces an engineering principle called idempotency. Idempotency guarantees that executing a specific operation 10 times produces the exact same result as executing it once. By applying a unique constraint to the intent ID within the database, the system physically cannot write duplicate executions. The second attempt simply bounces off. We enforce this using ACID constraints. This dictates that every tool the agent calls must either fully succeed and save or fully fail and roll back. We eliminate any partial states that confuse the agent's logic. When the agent blindly retries a completed task, the database rejects the duplicate execution but intercepts the failure. It uses a replayable envelope to send the original successful receipt back to the agent. The agent finally receives the confirmation it was waiting for. This satisfies its observe phase, fulfilling its prompt instructions and safely breaking the retry cycle. A language model's reasoning is probabilistic, meaning it will inevitably make mistakes. System reliability requires wrapping those unpredictable decisions in rigid, mathematical database rules. This diagram maps out how unmitigated feedback loops compound rapidly. In both sociological systems and software architecture, minor initial errors escalate through these interconnected circular paths, turning a single misstep into a structural collapse. In an enterprise environment, that collapse drains resources. When these loops compound, multi-agent systems can burn through up to 15 times more tokens than a standard chat interaction. A standard API failure might log a single error and stop, but an agent trapped in a runaway loop can execute 400 iterations in 5 minutes, draining your token budget while waiting for an observation that will never arrive. To prevent this, developers need to act today. Update all of your agent tool schemas to require an intent ID for every physical action. For the architects, you must mandate ACID-compliant transaction boundaries. Do not let an agent execute an external action without a database constraint acting as backstop. And for operations teams, implement structured logging via middleware hooks. You need to trace every single execution iteration to enforce hard limits on your loops. AI agents provide the intelligence to navigate complex workflows, but your infrastructure must provide the brakes. Have you ever caught an agent in a runaway loop? Share your worst debugging story in the